In this video, I want to explain the concept of Biot-Savart Law. You already know that from the Ørsted experiment, Ørsted found that magnetic field can be induced by the conducting wire. So here, Biot and Savart try to find how much is the magnitude of the magnetic field produced by a conducting wire. So then, Biot and Savart proposed Biot-Savart Law to calculate the magnetic field produced by a conducting wire as follows. You can see the detailed explanation of the Biot-Savart Law in this video. I also attached the link of this video in this slide. If we look more detail on the Biot-Savart equation, we can see here that the magnetic field B is equal to mu 0I divided by 4p integral ds vector cross r unit vector divided by r square. If we see more detail here, the magnetic field strongly depends on some parameters. The first parameter is magnetic constant or mu 0. Mu 0 is permeability of free space, and the value is constant, which is equal to 4p times 10 to the power of -7 Tesla meter per ampere. The second parameter which affects the value of the magnetic field is current, or I. And the third parameter which can change the value of the magnetic field is geometry and also the distance. Here I show you the first example how to find the magnetic field for a straight conducting wire. Let's say that I have straight conducting wire as shown in this green line, and we can see that the direction of the current of this conducting wire is to the right. We want to find the magnetic field at point P from the conducting wire, and the distance is A. We can understand from the right-hand rule, if we want to find the magnetic field at the position P, then the direction of magnetic field is out of the page. So from the Biot-Savart Law, we can easily find the magnetic field at P from the straight conducting wire. Following this explanation, please try to understand by yourself. Finally, we can find the magnetic field of a straight conducting wire is equal to mu 0I over 4pa cosine alpha b minus cosine alpha a. In a special case, if the wire is very long means that the length of wire, or L, is much bigger than A. In this case, we can simplify that the alpha b is approximately 0 and alpha a is approximately 180 degrees. So then we could find that the magnetic field for a long straight conducting wire B is equal to mu 0I over 2pa. We can also find the magnetic force due to two charged wires. Here we can see that each charged wires could produce the magnetic field, and the magnetic field is equal to mu 0I over 2pd. then we can find, for instance here, how is the magnetic force on I2 due to I1, and vice versa, using the Lorentz force. The second example, you can also determine the magnetic field for a circular current loop like this. So let's say that I have a circular current loop and I want to find the magnetic field at the P position here. Using the Biot-Savart Law, you can find that the magnetic field at point P is equal to mu 0 I A square over 2 A square plus x squared to the power of 3 over 2. And for the special case, if the x value is 0, means that I want to find the magnetic field at the center of the circular current loop, we can simplify the first equation to be mu 0 I over 2a, because x here is equal to 0. Another example is how to find the magnetic field for a curved wire segment. The same with the previous case, we can also use the Biot-Savart Law to find the magnetic field for a curved wire segment is equal to mu 0 I over 4 pi theta. And don't forget the theta here will be in radians. So the next example is how to find the magnetic field of a solenoid. A solenoid is a long wire wound in the form of a helix. You can easily describe the geometry of solenoid as shown in this slide. So how to find the magnetic field of a solenoid is also using the Biot-Savart Law. You can prove that the magnetic field of solenoid is equal to mu 0 n I over 2l cosine alpha 2 minus cosine alpha 1. So n here is the number of loops, because if we have a look at the solenoid more detail, solenoid actually consists of some number of loops. In a special case, if the solenoid is very long, means that A is much smaller than L, we can approximate the value of alpha 2 is equal to 0 and alpha 1 is equal to 180 degrees. So here is alpha 1 and here is alpha 2. So then the magnetic field becomes mu 0 I small n, with the small n is equal to capital N over L. The last example is how to find the magnetic field of toroid. A toroid is essentially a solenoid that is bent into the shape of a circle. Using the Biot-Savart Law, you can find that the magnetic field of toroid is equal to mu 0 small n I. Or you can also write down that the magnetic field is equal to mu 0 capital N I over P R1 plus R2. So that's the 5 example how to find the magnetic field in a different geometry. The last thing that I want to show you is about the magnetic flux. So actually the concept of magnetic flux here is the same as the electric flux, which we have discussed in the previous chapter. The magnetic flux can be calculated by using the equation BA cosine theta. And the maximum magnetic flux can be obtained if theta is equal to 0. Okay, so from this video, I hope you can understand the concept of the Biot-Savart Law and also magnetic flux.